I'm Daniel Braun from the University of Cologne, and this presentation is about novel visualization designs for large value ranges in time series data. The paper is a result of a collaboration between computer scientists of the University of Cologne and the King's College London. Time series with large value ranges are datasets whose values contain several different exponents in the scientific notation. They are common to a wide range of applications, such as medical data, for example, the history of COVID cases, with changes from 0 up to 300,000 in 1 year, or financial data like the Bitcoin price history. Common tasks for time series are the reading and comparison of values and the detection of trends. Especially in the lower orders of magnitude, it's very difficult to identify and discriminate values and thus to gain insights into the underlying data. For this reason, visualization techniques developed in previous research work well for smaller value ranges, but show weaknesses for large value ranges. Our designs are extensions of the logarithmic line chart and the horizon graph, which are standard techniques for visualizing time series. Our approaches are mainly based on a separate representation of the mantissa and exponent, and a linear scaling within each order of magnitude. To get a better understanding of our designs, let's take a look at the step-by-step creations. The standard logarithmic line chart is the basis for our so-called order of magnitude line chart. In the first step, we linearize the scaling within each order of magnitude to allow for a more intuitive reading of the axis. In addition, we add a value-by-value coloring of the area below the line using the order of magnitude color scheme. This results in a double encoding of the underlying values. An individual value can now be read either by looking at the position or the color. For the order of magnitude horizon graph, short OMH, the first two steps remain the same, so that the log line chart with linear axis scaling is the starting point. Instead of coloring individual values, we now color the area below the line by using a different hue for each order of magnitude. As the last step, we layer each order of magnitude in ascending order, as is common for horizon graphs. As a result, the mantissa is mapped to a single linear scaled y-axis and the exponent is mapped to color. This mapping can now be used to read individual values. We compared our two new approaches in a user study. In this, we compared our two designs with two of the standard techniques for visualizing time series data, the log line chart and the standard horizon graph, as well as with the scale stack bar chart, which is a standard technique for visualizing large value ranges. In the study, we measured accuracy, response time, and the confidence of the participants in their answers. In total, 90 participants took part in the online study. There were no significant differences in the self-reported expertise, and all participants were from a university environment. We identified 4 main tasks based on our initial challenges, which are a combination of common tasks in large value ranges and time series research. In the identification task, the participants had to read individual values. Whereas in the discrimination task, they had to decide which of two values was larger. In the estimation task, they had to determine the exact value difference. The last task was to detect specific trends. For the main results, we first have a look on the error rates per task. Comparing our two new approaches, the order of magnitude horizon graph performs better. For identification, discrimination, and estimation, OMH outperforms all other designs with very few errors in total. Statistically significant is this improvement of OMH in the identification task compared to the log line chart and the standard horizon graph, and in the estimation task compared to all other designs. Only for trend detection, the standard horizon graph has a lower error rate. Moreover, the order of magnitude horizon graph increases the confidence of the participants in their answers. This provides an additional qualitative indicator for the subjective trustfulness of our visualization, in addition to the quantitative measures. Significant is this increase of the confidence with OMH in the discrimination task compared to the standard horizon graph and the scale stack bar chart, and in the estimation task, again, compared to all other designs. For the response times, there were no significant effects at all. Nevertheless, OMH was among the best in any task. In future work, we would like to examine the encoding of positive and negative values with our approaches. Furthermore, it would be interesting to investigate large value ranges in multiple time series. Based on our study results, an improvement of large value ranges visualizations for trend detection might also be useful. In summary, we introduced two novel visualization designs for large value ranges in time series data. They extend standard techniques and use a separate representation of the mantissa and exponent of a value. The order of magnitude horizon graph outperforms all other designs in reading and comparison tasks, while the linear scaling of the classic horizon graph leads to better results in trend detection. Moreover, our new designs increases participants' confidence without requiring additional time to understand them. I thank you very much for your attention.